In this second lesson of the 5th section of the study of wave phenomena, what I am going to do is to introduce, analyze, describe and apply what is known as the Doppler effect. In addition, I am going to analyze different situations in order to be able to arrive at a mathematical expression that allows me to quantify it, and I am going to finish by showing some examples of application. To begin with, I would like to say that the Doppler effect was discovered in 1842 by the Austrian physicist and mathematician Christian Andreas Doppler, who observed that when there was a relative displacement between a source emitting waves and an observer, a change in the detected frequency occurred. A situation that represents what Doppler experienced. We have it here where Amanda is at rest in a certain space and detects that the sound that comes from an active siren of a vehicle that is in motion is very different when the vehicle is approaching her or when the vehicle is moving away. To analyze these situations, I am going to take advantage of these diagrams, where what I am going to consider is that an emitting source is emitting a sound, and I have an observer that can be at rest, the movement can be found, or the source itself can be found moving. I do want to emphasize that when I speak of waves, they do not necessarily have to be sound waves. The Doppler effect is associated with any type of waves, sound, electromagnetic, whatever their nature. Let's start by analyzing these situations just to begin with. I have an observer that is at rest, and I consider a wave-emitting source that is approaching it and moves to the right. And another situation what I have is a wave-emitting source that is at rest, and I have an observer on the right that is approaching the source, while the observer on the left is moving away from the source. We observe that the wave fronts change. On the left, I have that the wave fronts have smaller distances to the right of the emitting source, while on the left, these distances are larger. What happens then? The pulsation detected by the observer on the right or on the left changes. On the other hand, in the diagram on the right, the observer on the right moves closer to the source, while the observer on the left moves away, and the same thing happens. The pulsations then detected by both observers also vary. We can also consider the case where both are moving, both the source and the observers, and of course the pulsations or the detected frequency of those waves will also change. Let's try to quantify what's going on. Try to determine the frequencies determined by the observer using these diagrams. I'm going to start with the premise where what I consider is that the emitting source is approaching the observer, and the observer, in this case, we start by assuming that is at rest. Velocity of the observer is 0, therefore, and velocity of the source is moving to the right, in this case, approaching this observer. The wave fronts will therefore present this geometry that is represented by the red circles, and if we try to measure the wave fronts that will reach the observer on the right, the distances that will be between those wave fronts will be smaller than those of the wave emitted by the source if it were at rest. The wavelength itself that would be defined by the velocity of propagation and the period of the wave, in this case will be described by the distance that is actually being detected to the right of the emitting source, by the observer on the right therefore, but to that distance it should be added to take into account the entire wavelength of the wave, the speed of the focus times, the period that will give us the space that has moved to the right of the emitting source. We have therefore that this distance is given as a function of the difference of these two terms, where if I take out of common factor the period and express it as a function of frequency from its inverse, I have this mathematical representation for the distance. I will now consider that the observer also moves to the right. Therefore, this distance that I have determined before. Now it turns out that the new position of the observer forces me to also take into account the distance that he has moved to see when the new wave front reaches him, and that distance will be determined by the speed of the observer and the period of that wave that he is detecting therefore. Therefore, the distance now that I had previously determined from this expression, I can now represent it as a function of the difference of these two terms, where I take into account the period to which would be the period detected by the observer, and as I have done before, I can put it as a function, from its inverse with the frequency detected by the observer. Taking into account the two mathematical terms, I arrive at this representation, where what I can conclude is that the frequency f detected by the observer is determined from the characteristic parameters of the emitted wave, its frequency and the speed of propagation in the medium in which it is, but I also have to take into account the speed of the source and the speed of the observer. Now, I will be able to explain and quantify the effect that I was determining in the drawing at the beginning, Amanda, where she was detecting different frequencies. In the case where the emitting source is approaching her, in this case, an ambulance with the source, with the siren active, is approaching. The frequency that Amanda is detecting is higher than the frequency of the sound that is being emitted. It is a higher pitched sound, while when she moves away, the sound she is receiving is more deep. Another application of the Doppler effect is when we are, for example, in an open space, and we detect the sound produced by the engines of an airplane. That sound will depend on the speed of the sound source of the plane. In this case, that plane may be moving at a speed below the speed of propagation of sound in that medium. I'll talk about a subsonic speed, or maybe moving at the speed of sound that is technically called a speed corresponding to Mach 1 or a higher speed, corresponding then the speed of the plane to a supersonic speed. What happens in the latter case is that the wave fronts that are being emitted of sound will be superimposed and will define this cone that I am trying to represent here. In this cone, what is happening is that the wave fronts are being superimposed, and therefore the energy associated with these fronts of all the waves that are being emitted. And when this superimposition of energy reaches the position of the observer, in this case where we have placed Amanda, what is going to happen is that the energy will be superimposed in the cone. What is going to happen is that the perception of the sound is as if there was a burst, because there has been an accumulation of all the energy associated in this case to all the noise that the airplane engines are making. Another example of application of the Doppler effect is in astronomy. It was in 1929 when the cosmologist Ewan Hubble was looking at the characteristic galaxy spectrum and realized that those spectra actually had a redshift towards longer wavelengths. If we try a little bit to look at the visible spectrum, it turns out that we will go to longer wavelengths if we go to the red and shorter wavelengths, to the blue or the ultraviolet. Well, Hubble realized what was happening with the images taken of galaxies by observing images such as this one I have posted here, and concluded that this displacement was due to the fact that the universe is not static but is expanding. In astronomy, the Doppler effect is also used to analyze binary systems of stars that are orbiting with respect to a common center. Another application is in medicine, where thanks to the observation of images and see how the blood flow is moving, thanks to the Doppler effect, it is explained how that flow is being produced, and thanks to that it is possible to determine heart disease in certain organs of the body of different living beings. As an example here, I have put a study that was being done through an echocardiogram that represents the blood flow in a mitral valve in a dog. At this point, we have seen how, thanks to the analysis we have made of the Doppler effect, we can determine the frequency change that occurs when there are relative displacements between an observer and a source emitting waves. And that frequency will be perfectly determined, knowing the frequency, the propagation, velocity of the wave in the medium in which it is, and also knowing the speed of the source and the speed of the observer. If any of the two does not move, the corresponding term will be zero. And also we already know some direct applications where the Doppler effect is widely used. Thank you very much.